most of us are familiar with the narrative of how the universe began. There was an infinitely dense point of infinite temperature with no size called a gibber. This gibber exploded, creating all the space, energy, and matter that we consider to be our universe in an event called the Big Bang. Between 10 to the power of negative 36 seconds and 10 to the power of negative 32 seconds, space expanded rapidly, growing much larger in size. After this period, space continued to expand but at a much slower rate, and eventually, we see the universe that we observe today. This is the inflationary Big Bang theory, the most popular and broadly accepted theory of how the universe began. However, for a few physicists, the premier theory does not paint an accurate picture of the origin of our universe. Rather, they say that the universe existed before that point, stretching into the past as well as the future. While the universe is expanding today, it was contracting in the time before the Big Bang. In this picture, the Big Bang isn't so much a bang, but a bounce, a moment when the universe reversed course and began to grow. According to their theory, the universe could bounce again. Today's expansion could be followed by a collapse in the far future, followed by another bounce. Some physicists have suggested this bouncing could be eternal. This, of course, is counter to the way most cosmologists see it, where everything started with the Big Bang. Renowned physicist Brian Cox also challenges the Big Bang theory, arguing that something cannot emerge from nothing. Adding a bit of tension, the James Webb Space Telescope has made a bunch of unexpected discoveries that challenge the notion that the Big Bang marked the beginning of the universe. All of these raise a question: if the Big Bang wasn't the beginning of the cosmos, then what was it? Could the universe start with a bounce or something else entirely? Join us as we dig deep into one of the thorniest ideas in cosmology, the idea that the universe had a beginning or a day without a yesterday, as it was originally known. This concept goes all the way back to Georges Lemaitre in 1927. Although it's still a defensible position to state that the universe likely had a beginning, that stage of our cosmic history has very little to do with the hot Big Bang that described our early universe. Although many laypersons, and even a minority of professionals still adhere to the idea that the Big Bang means the very beginning of it all, the reality is more nuanced. The Big Bang now is not the beginning of time and space as we know it today in 2023. In fact, there's a lot of evidence that points to a non-singular origin of our universe. We never achieved those arbitrarily high densities and temperatures thought to occur at the Big Bang. Instead, our universe is best described by an inflationary period that occurred prior to the Big Bang, and the Big Bang is the aftermath of what happened at the end of inflation. Let's walk through what that looked like. During inflation, the universe was completely empty. There were no particles, no matter, no photons, just empty space itself. Yet that empty space had a huge amount of energy in it, fluctuating over time by about 1 part in 30,000 on average. As the universe inflates, expanding in a rapid, relentless fashion, those fluctuations get stretched to larger scales, while new small-scale fluctuations are created. This pattern of fluctuations from small scales to intermediate scales to large scales, or top superhorizon scales, is one of the defining predictive features of cosmic inflation. This continues as long as inflation goes on, but inflation will come to an end randomly and not all at once. In fact, if you lived in an inflating universe, you'd likely experience a nearby region where inflation came to an end, while the space between you and it expanded exponentially. For a brief instant, you might even be able to detect what happens at the start of a Big Bang before that region disappeared entirely from view. In an initially small area, perhaps no bigger than a human handball but maybe even much larger, the energy inherent to space undergoes a transformation into matter and radiation. This conversion process happens relatively quickly, taking approximately 10 to the power of negative 33 seconds or so, a brief period but not instantaneous. As the energy bound up in space itself gets converted into particles, antiparticles, photons, and more, the temperature starts to rapidly rise from just a few degrees above absolute zero to perhaps around 20 Kelvin or so over that same short time interval. Due to the substantial amount of energy converted, everything will be moving close to the speed of light. All quantum particles, whether massless or massive, will behave as radiation under these conditions. This conversion process is known as reheating, signifying the end of inflation and the beginning of the hot Big Bang. At tremendous speed, you'll witness a tremendous change from all prior conditions. When the hot Big Bang first commences in the universe, space expands exponentially with more distant regions accelerating away relentlessly. However, when inflation ends, the universe reheats and the hot Big Bang begins. More distant regions will now recede from you more and more slowly as time goes on. From an outside perspective, the part of the universe where inflation ends sees the expansion rate drop, while the inflating regions surrounding it see no such drop. Under inflation, the distance to any object would double after a certain amount of time, and once that same amount of time elapses, the distance doubles yet again, and the process is relentless. But once the Big Bang begins, all of that changes as the universe immediately slows down after the first moment of expansion elapses. This is why it's extremely likely that from the perspective of whatever region of space you're in prior to the Big Bang, you'll experience inflation ending in nearby regions many times. These locations where inflation ends will quickly fill with matter, antimatter, and radiation, expanding more slowly than the still inflating regions. In the inflating region, as a typical region within space-time dominating its volume, these regions where hot Big Bangs occur will recede away from all the other locations where inflation still goes on exponentially, meaning they will very quickly recede from one another's view in the standard inflationary picture. Because of this expansion rate change, there's virtually no chance that any two regions where separate hot Big Bangs occur will ever collide or interact. Finally, the region where we will come to live gets lucky, and inflation comes to an end for us. The energy inherent to space itself gets converted into a hot, dense, and almost uniform sea of particles. The only imperfections in uniformity correspond to the quantum fluctuations that existed and were stretched across the universe during inflation. The positive energy quantum fluctuations correspond to initially overdense regions, while the negative energy fluctuations get converted into initially underdense regions. Yet, that's still enough to serve as the eventual seeds of cosmic structure. We cannot observe these density fluctuations today as they were when the universe first underwent the hot Big Bang. There are no visual signatures we can see from that early time. The first one we've ever accessed is from 380,000 years later after they've undergone countless interactions. Even at that point, we can extrapolate back to what the initial density fluctuations were and find something consistent with the story of cosmic inflation. The temperature fluctuations imprinted on the first picture of the cosmos, the cosmic microwave background, give us evidence of how the Big Bang began. However, there are a lot of inconsistencies between the cosmic microwave background and our current model of cosmology. These can be summarized in 4 points. First, on very large scales, the universe isn't acting like we think it should. Second, light from the cosmic microwave background will be lensed by matter in between us and the cosmic microwave background. This means that matter acts like a giant lens, bending and amplifying the amplitude of the light behind it. The amount that this happens is not consistent with our current model of the universe. This is such a significant problem it has sometimes been called a crisis for cosmology. Third, the two halves of the cosmic microwave background sky have different average temperatures. This doesn't make a lot of sense since we believe that the universe should have started out uniform on average. Fourth, the value of the Hubble constant, which describes how fast the universe is expanding, is different whether we measure it from the cosmic microwave background or from more nearby celestial objects. Taken together, these issues mean we're missing something fundamental in our understanding of the universe. The answer may lie in loop quantum cosmology, a theory derived from loop quantum gravity. In loop quantum gravity, gravity itself is made of particles called gibber, which come together to form the fabric of space and time. In this model of the universe, there is a smallest size of space itself, the Planck scale, or 10 to the power of -35 meters. Nothing, not even space itself,